It's very nice to be here. Thanks so much for inviting me, Abubakar, and for these kind words. So yeah, today I want to talk to you about diffusion models. Maybe you've heard about that. Those are the models behind DALL-E 2 and Stable Diffusion and many other cool applications. But they don't only make images, but they also can make uh, videos. That now we've seen those. Maybe you saw some text to video examples from Meta and more recently from Google Imagine Video. Amazing stuff. And yeah, and those all work with diffusion models, which are a class of machine learning models, unsupervised learning models, but with a very distinct flavor to them. I will just ask maybe Barbara or Abubakar to allow me for sharing my screen, if that's possible. Oh, I'm allowed. Okay, great. I can see that. Let's share this now then. Okay. Can you see my screen?
Yes.
All right. So this will not be a super in-depth talk, and also I want this to be a conversation. So I will go over the slides and then we can have a chat. But the idea is to explain a bit how diffusion models work on a high level. So yeah, essentially, as you can see in this cool example from NVIDIA, diffusion models are a process where you turn noise from image. So you denoise it step by step. And where did it come from? Well, it came from non-equilibrium thermodynamics, which is a weird place for machine learning models to come, I thought. But after realizing what it does, it makes a lot of sense. So essentially, in 2015, this paper, Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics, was out. And basically, it was showing how you can train a model to do non-equilibrium thermodynamics. So basically, you have this 2D particles here that spread like a gas, if gas could spread in 2D, kind of. And then you would train a model to like try to reverse the step to get back to the order, right? So like an entropy reversion process. And this was cool. It got a bit of attention at the time, but there were not that many applications. GANs were really big at that time, and everyone was looking at general adversarial networks. And then, yeah, from 2015 up to 2020, not much happened in that field, but then this paper got out in June 2020, Denoising Diffusion Probabilistic Models, the DPM, and that made a huge impact because essentially it showed how it reached close to state of the art in many data sets for image generation. So we're using the same logic, but adding a denoising score. So essentially they added a score to see how, like a loss function to see how good the denoising process was. And this improved a lot from this paper to this one. And that became attainable and maybe even competitive with other generative models. Then in June 2020, yeah, essentially this is the process, right? So this is the same paper. So the denoising process works a bit like that, where basically you would want to add a little bit of noise at every step and train the model to learn the previous step. So instead of like going all the way from noise to image, you go step by step and you train the model one way and then you train it to reverse that. And that works. That worked really well. But of course, the architecture of the neural network is a UNet. After all, this is still a deep learning process. So you have a UNet that essentially learns how to noise and denoise these images, and that's the process with this denoising score that made this paper from 2020 of the method DDPM get a lot of traction. So one analogy I like to make about diffusion models is this Michelangelo quote that says that saw the angel in the marble and carved until setting him free, right? So basically, you have like a block of noise, and then behind the noise, the model is really trying to find the model. Actually, this was not him, of course, like any internet quote. This is not true, but I think the analogy still holds. So I like using faking quotes that make it go really well with what I want to say. So yeah, so then the diffusion model started picking up, and they joined the club of generative models. So together with GANs, with VAE, now diffusion models were there in the club of good models or state-of-the-art or models that are worth paying attention to. And from then we saw an explosion. So we stayed 5 years without many advancements, and then, as we can remember, it's June. So from June, then we saw October. We had, well, what if we did sample this the DPM without the Markov chain? And this is the DIM. And they found out this could be 10 to 15 times faster. Then they asked what happens if they added a few tricks and modifications to the DPM. It was faster and had the same quality. Then OpenAI released this paper that got famous at the time because it had a very bold title, which was Diffusion Models Beat GANs on Image Synthesis, which essentially they asked, what if we guide the diffusion process with a classifier guiding the gradients, and that beat GANs on most of the use cases. Then in July 2021, a new paper was out talking about classifier-free guidance. So basically what happened if you use the classifier guidance, but some non-classifier guidance, and turns out it was actually better quality. So while this was happening in academia, while all these papers were coming out, text-to-image was picking up. So in January 2021, the DALL-E 1 blog post was out together with the Clip blog post from OpenAI, and Clip was released open source while DALL-E 1 wasn't. But with Clip, people are using Clip to guide gradients for GANs using Clip as a loss function, and that was already enabling creative explosion for text-to-image. And from then, well, wait a second. So they were using Clip to guide loss or gradients as a loss function. So Catherine Krausen essentially asked herself and then implemented, what if we guide the diffusion process with a Clip loss? And then we saw a second wave of a creative text-to-image explosion, which was called Clip-guided diffusion. So this got kind of mainstream, and then community-driven efforts appeared and took over a niche corner of the internet in mid-2021 with these amazing capabilities of generating images. You might have heard about Disco Diffusion and others. And well, with that, essentially OpenAI and the whole academia in this industry were kind of taking notes of what the community were doing. And they released Glide, which was like basically what if they apply classifier-free guidance to condition image generation with text. And they found out it worked really well. And they and then also Latent Diffusion, which is the base for Stable Diffusion, by the way, which they essentially apply the Glide model, but on the latent space. So they use the latent space that is 8 times smaller than the pixel space to do the diffusion process. With that, as we see this explosion happening, DALL-E 2 was out, and essentially DALL-E 2 was very similar to a bunch of community-driven Clip-guided diffusion processes, but they worked very, very hard to make it more efficient. But it's interesting to see how the open source community informed a little bit of what OpenAI did to release DALL-E 2. And then Imagine by Google essentially turned the architecture way simpler, and they added a frozen text encoder to improve the language understanding, and that like beat DALL-E 2 in quality based on the cherry-picked examples we see, because the models are not open source. So diffusions are here to stay, but it's a bit messy. So diffusion processes have models, schedulers, pipelines, but each implementation kind of does it on their own way, and the academic repositories are not really maintained. That's why Hugging Face released the Diffusers open source library, where essentially the idea is to combine models, schedulers, and pipelines in an inter-exchangeable manner and make sure that all diffusion models can be ran and executed, similar to what the Transformers library does for natural language processing and for vision, but with diffusion models instead of transformers. And with that, we arrived at open source state of the art, which is Stable Diffusion. Stable Diffusion is a latent diffusion process with a frozen flip text encoder, which is a trick from the Imagine paper that I just showed before, trained on a bigger data set than latent diffusion and for more stats. And that, yeah, essentially took over the internet. You might have seen a lot of examples and demos and memes about this, and maybe you'll use it as well. But yeah, this is where this comes from. It comes from this latent diffusion models that on its own came from the diffusion models, which are a class of models that work by adding noise to an image and training this model to learn what's the previous step. And this all came from non-equilibrium thermodynamics from physics. And yeah, essentially this creative explosion is unfolding with diffusion models. 1 week of Stable Diffusion, we had dozens of applications and integrations emerged. And now that we have like a month, this has even gone crazier. And that's just the start. Overall, I think this is the start of a very distinct future where we will essentially use machine learning and more generally like machines or computers to tell us what we want, and they will just assemble for us. So if you think no code on programming, you can think of no interface on like a Photoshop that you use words only, or video editing where you use words only, or even you don't need to edit the video because you can generate the motion picture. So you can write a script and turn the script into a video directly. So like you can just imagine a movie and have it come out, or you can imagine like an ad and have it come out. So this will empower human creativity on non-precedented levels because you remove the barrier of having the skill to do it. Of course, there are challenges there in regards to how would artists react, but at the same time, it's opportunity for them to, I think no one but artists is in the best position to use this as tools and beat everyone in what they are making. So yeah, these are a bit of the reflections that diffusion models bring us. And yeah, and of course, this is one class of models like I've shown before. So GANs and VAEs are still very important, and they are so there are ways of combining them as well. There are people using them to be combined, but definitely diffusion models join the pack to stay. That's for sure. So that's a bit what I had to expose or show to you. I have a bunch of resources here as well that you may pick up later. I will make sure you have access to this slides as well. And then, yeah, thank you very much. And I'm open to questions.
So we have one question that was asked in the chat already. I don't know if you can see it, or if you want me to read it to you here. Do you see the ResNets question?
I just opened it. Yes. So John F asks, ResNets are part of UNet. Why can't we just have ResNets as our neural network model instead of UNets? What's special about UNets to make them good at this task? That's a good question. I think that it's just a simpler architecture, right? Because, well, I'm like, I'm not completely sure because I don't know whether someone tried to use ResNets for diffusion. I know that the clip model had a ResNet version and a VIT version, and they preferred the VIT because it performed better. But the clip model is not a diffusion model, so it's not really an answer to that question. But on the model side, what I know is that what I tried is that UNet really worked well. So maybe that's a research avenue to check out why doing that. But yeah, and also like what Siddhar answered, that the size of the image. So on most of these models, they can do around, like, with a reasonable computation, they go from 64 to 256 pixels. There are some models that are 512. And the latent diffusion process brings this to the latent space, and then they can do operations 8 times smaller. For example, with DALL-E 2, the actual images out from the diffusion models are 64 by 64 pixels. And then they have 2 upscalers. They have one upscaler that goes from 64 to 256, and another upscaler that goes from 256 to 1024, which is what you get if you actually use DALL-E 2. But so Andres, what's stopping us from having larger image outputs? I think the answer for your question is, it a hardware or model constraint? I think it's both. It is a hardware constraint because if we use the current models, we wouldn't be able to train these models on bigger images efficiently with the current hardware that exists. So essentially, that's a bit of both. The answer is both, because if the hardware was better, we could train more bigger images. But if the models were more efficient, you could also train bigger images. So it's a bit of at the moment we landed, I think the models can do 1024 maximum if you do latent diffusion, or if you do upscaling up to 1024 as well. But there are, I think, with upscaling tricks and the upscaling models, because you can also train diffusion models to do upscaling, this can be an avenue for getting bigger, as well as potentially exploring smaller latent spaces than the latent diffusion space. I don't think there's anything theoretically stopping us from trying to train an even smaller latent space that then recreates the image. I guess that should be tried, but I don't think there is a theoretical limitation. So that could potentially be the case. So John asked, what do you use the schedulers for? I've seen examples where they're swapped out. What are we trying to achieve by using a different scheduler? So essentially, the schedulers, what they do is that they do the denoising process. So here, if we see this, the scheduler is the tool that is doing this, this process here. So you go from noise all until you get the signal again, right? And basically what it does is that when you're denoising the image, you can have a different mathematical techniques to do it. So you train the model on noising and denoising, but you can do use different models to do the denoising process, and we call those schedulers. So the reason why they're interchangeable is because you could have different ways to solve. This is the denoising process is essentially a differential equation, and you can have different ways to solve that equation. Some linear, some non-linear, some exponential ways, and each of them can have advantages and disadvantages, because basically the point is, once you get the same noise, ideally with the same scheduler and infinite, with all schedulers and infinite steps, you would have the same image process. And yeah, so essentially that's what the process of the schedulers do. So John F asked, one of your slides mentioned the guidance scale. What is that? So a guidance scale, and let's go here to the slide where I mentioned that. Guidance. I think it's the guided diffusion one. I'm not sure if I have a slide that talks about guidance scales, but I can talk about it anyways. So essentially the guidance scale is how strong at least on image generation models. So like, for example, when we do this, generate an image from a model, the guidance scale is the score that you use to say how strong the model, the prompt will influence in the guidance of the model. So essentially, when you have the prompt for the image to be classified or to condition the model, you have here so if we come here to these models that have the guidance on text, what we do is essentially that the guidance scale is a scale that says, well, if it's 0, then it's just an unconditional generation, and then if it's infinite, it would, in theory, be exactly what your prompt says. But of course, it starts degrading, so you want to do something in the middle. Another question. Sorry, I thought the UNet does the denoising. Could you distinguish from the scheduler, please? Yeah. So essentially, the UNet does not do the denoising. What it does is that it learns. So the UNet architecture will essentially learn the characteristics of the model. So it will learn the denoising process itself. So basically, during a training phase, you will train the UNet, and the trained UNet will learn how to essentially do the process in reverse. So it will learn how to do the from noise to image, and therefore from image to noise step by step. And once that UNet is learned, you will initialize a random image. So you will initialize with Gaussian noise an image, and then you will need the scheduler to actually do the denoising process for the UNet. So essentially, you are training the UNet using the scheduler, the diffusion scheduler. So it is the UNet, but the UNet is not in one step because of how diffusion models work. You can't simply do the process in one step. So you use schedulers to do this process step by step, and each step you will essentially throw the model in the UNet and get the output, and then redo the noise and keep doing this iteratively. So what diffusion models do is that they add the iteration process, which is something that other machine learning models didn't necessarily do. Once you're trained, you could just like do it in one step, generate your output in one step. But with diffusion models, you need to get the noise, and then you throw the noise and into the UNet with what's the next step, and then you'll get a slightly less noised image, and then you do it again multiple times. And the way to do it more efficiently, instead of naively doing, because you train a diffusion model on let's say 1,000 steps, but it would be very inefficient to reverse that process with 1,000 steps again. So there are some mathematical tricks to make that faster. I also have two other questions that are not in the chat but in the QA. there any work being done regards using diffusion models in conjunction to nerves to do something like 3D model view and synthesis and generation? Yes. Yes, and that's a very exciting field because today an open source model was released to do text to 3D based on Stable Diffusion. So Google released a paper called Dream Fusion, which essentially, it doesn't use nerves actually directly, but the output is indirectly with nerves. But essentially, it gets one image generated by the model, and then it can generate all the other angles of view and generate a 3D model from that. So that's one way of doing diffusions with 3D, and that's a very exciting process. You should look for Dream Fusion and the Stable Dream Fusion, I think it's how they called it, which is really good naming for that, and that's one way. Another more classical way that some people are doing with 3D is essentially training a 3D UNet and a whole 3D denoising process. So a little bit like the Marble Angel example, where you would have a 3D space and then a denoising process. So you would need hundreds of 3D objects to then train a model on that. But I don't think that's that advanced. I think the most recent text to 3D advancements are either using clip to optimize for nerves and other objects, meshes and things like that, but those don't necessarily use diffusion. And then this model that was out today, the Stable Dream Fusion, uses the image generation process for Stable Diffusion to actually generate novel views on 3D. I don't have it right fresh in my mind the exact process, how it works, but you can look into that, and it's really fascinating. So there's another question. Do you see any non-image applications for these models that will happen in the near future? Yes, and not only in the near future, but they're already here. Audio, for example, as mentioned. The diffusion process is quite agnostic on whether it's applied on image, audio. It's really multimodal because essentially the idea for these models is that you can anything that you can add noise to for it to learn a class of examples, and you can train it to denoise, it can be used. So audio, of course, makes a lot of sense because it's even simpler. You can do a 1D UNet to do a lot of noise in the audio and then learn to denoise it. And actually, there are quite a few audio diffusion models, but they're not that good. And some people say that it's because there is less interest in researching for audio diffusion models. But other people have a hypothesis that I think is fascinating, that it's actually audio and image are actually more or less at the same place, but it's just that our eyes are more forgiving with images. So for example, these images look cool, but if you look really deeply enough, you'll see that a lot of things on them are off, right? Like it's not really perfect, but when we have audio, essentially, if every small detail that is off is really perceived. So we are just, as humans, less tolerant about how this works. And in audio, so our threshold or bar is higher for audio. But there are models out there already, audio diffusion. They're not text conditioned yet, so you just train them on a bunch of drum beats, and then it generates back some drum beats for you, things like that. But like typing a song by Lady Gaga in the style of Iron Maiden is not, we're not there yet, but we're not far from that either. Like that's text conditioning audio, and we have a lot of labels, even like the lyrics. So that's definitely something that we should expect in the next couple of months. As well as other examples of other applications are video, 3D as mentioned, and even in other fields. For example, molecules in DNA, molecules are being generated using diffusion models, as well as human movement. So there is a fascinating paper that had the code out today as well, with human movement, so text condition human movement. So you would type a person picking up a box, and then it would generate like a person doing this, or the joint. I don't know what's the technical term for the 3D artist, that like the joint movement of that are very realistic that you can then apply to a 3D model. So that's coming, and yeah, molecule generation as well based on learned processes for diffusion. So many fields and very distinct applications. Can you talk more about latent versus pixel space? How introducing a latent space improves performance, and how do we go from latent space to pixel space? Great question. Let's go. So on latent diffusion and then stable diffusion, that uses also the same technique. The latent space is more efficient because it improves performance because it's smaller. So essentially what happens is applying the diffusion process is a computationally expensive process. So that's why it's faster to do it on 32 by 32 images than on 512 by 512 images. So what the latent space does is that it's almost like a compression algorithm. So it turns an image that is on pixel space into a representation of that image that is 8 times smaller. So you move from pixel to this latent space that is 8 times smaller, and this latent space is then compressed using a VAE. So when we talked about merging classes of models, so you have a VAE that essentially does the encoding and decoding of the latent image. And the latent image, so while the pixel space has 3 channels like RGB, on the latent space it's 8 times smaller with 4 channels. And essentially you can reconstruct the image with it's lossy, but it's not necessarily the loss is like better than JPEG, for example. So it's a really good way to represent a model, and that's how you can do that. So some more questions from the chat. Sorry, I'm going back and forth between the QA function and the chat. Lucar asked, can you talk a little about textual inversion and the Stable Diffusion concepts library? Absolutely. So the textual inversion is a technique built on top of Stable Diffusion that essentially made it a very clever thing that creates a new vocabulary. So you create a new token, a new word, and you train the model to learn a concept based on that word. So essentially, let's say when the model was trained, the weird Sonic movie, if you remember that, wasn't out yet. And then you really want to use that weird Sonic in your prompts, but the model wasn't trained for that. So what this does is that you create a new token, you call it like Ugly Sonic, and then you show the model a few images, like 3 or 5, it's very little. And essentially you make the model try to invert that image. So like search in the latent space of the model, the closest matching images that the concept that you're showing the image for are. And after like 3,000 to 6,000 training steps, essentially you get a text embedding. So you get a 4 kilobyte file that learn this new concept, and you can use it in the model to train it. Maybe I can show it to you. Can you still see my screen? Because I don't know if I shared the...
Yes.
Okay, so essentially what we have here is this process, and then we have a public library of community trained concepts that the community essentially, and of course it's not going to work because it's a live demo. Oh, here it is. So yes, essentially we have a library of concepts that people train that you can use in the Stable Diffusion model. And you can use both styles and objects in this technique. And then essentially, maybe the model doesn't know how Super Mario World maps are, or this particular artist style, and then you can essentially say, for example, okay, so it works. But like, let me get to the other questions while this is being generated. So the scheduler is like a time step. It's telling you the number of times the image passes through the UNet model. That's right. That's right. That's what it is. So essentially, and every time it passes through the UNet model, it has a little less noise to it, added to it, and then the UNet model tries to predict what's the output until when you have like time step t minus 49, if you have 50 steps, you get to almost a little noise, and then the UNet can fully denoise the image. Any idea why the recommended images are always 512 by 512 and not another size? Well, this is just a confluence of reasons. So on Stable Diffusion particularly, it's because this was the image size that it was trained on. So in Stable Diffusion, it was trained on 512 by 512 images. So if you go lower, the model kind of breaks. And if you go larger, the model loses coherence. So like if you ask for a dog, you might see a dog with two heads because it doesn't have spatial coherence above the level that it was trained on. So that's a bit why this model. And then other models were 512 for different reasons, but I think overall it's like a confluence of like what was reasonable to train on at the hardware that we have available right now. So things converge a little bit to that size. So the website is multimodal.art. And yeah, the demo is taking a while to load. I think it's not gonna load right now, maybe. But yeah, essentially you can train. Here is the ugly Sonic, by the way. You can train these embeddings on new concepts, and then you can use them on your prompts. And yeah, I encourage you to try it. And yeah. What else? Do we have more questions? I think we're done with questions. Does anyone have any more questions? I think we have 10 more minutes. I guess not. In this case, thank you so much. I really appreciate it to having had this talk to you. It was really great. Am I still sharing my screen?
Yes, you are.
Okay. Okay. Thank you so much for your time and for your attention. It was really great to have you and to talk with you all. Thank you all that sent questions or that participated in any way. And I will send the slides to Barbara and to Abubakar. And also you can find me on Twitter. It's at multimodal art. Here it is, where we can keep in touch. And if you have more questions or if you have cool projects, I'm happy to collaborate on, because I think this space has a lot of ideas, and sometimes it lacks like this level of abstraction up of like things combined. So yeah, I'm trying to do that with information organization and with overall space management and novelty bringing to every one of you. So thank you very much, and
Thank you, Foley. We'll get the slides to you shortly. Thank you so much for